I was saying how grateful I am to Rahul for having given me the opportunity to come and listen to a large variety of interdisciplinary talks. This is the picture of India, and those light points also give you an idea of the 1,200 million people that inhabit India, but you might notice that there's a preponderance of that light right here, at the very edge of India, which is ramming into Tibet. And Tibet is on average about 4.5 kilometer altitude, very large plateau, the largest in the world, thousands of kilometers laterally. And India is running in, and those numbers tell you that there have been earthquakes all along this boundary in those years as well as here. So that's how it's going forward. Would this work? Oh, sorry.
Somebody, we can't find the...
Oh, that's okay. That's okay. This is a picture of some buildings in Tokyo which swayed during the earthquake at Fukushima, and many of you might have heard about it because there's a nuclear reactor over here, which wasn't damaged by the earthquake, but it was dredged by the tsunami, so the pumps were put out of action. And that was because of the reactor melting down. But the buildings in Tokyo, some of them swayed by quite a lot, several tens of centimeters. And Honshu, which is the island on which Tokyo is, that part of Japan, was shifted east by 2.4 meters. And actually the Earth's axis also shifted by 10 centimeters. So in order to conserve the angular momentum. So this was the severity of the mechanical instability which was caused by this particular earthquake. The buildings, those are the ground motion before it, but the buildings swayed and were still safe. Therefore, as I said in the very first this thing, that 1,200 million people, but we are heirs to an unprecedented stock of knowledge. And I think that's a very important message to take, because what distinguishes one society from another is not the knowledge that it has, but what it does with that knowledge. And on that count, there's a great deal to be desired in this country. I don't know why culturally or otherwise. It was known for a long time that earthquakes do visit different parts of the world, and that they must be the result of some kind of mechanical instability. But it was only in 1906 that it became quite clear that they are caused by fractures in some part of the earth. Now we know it's in that part of the earth which is cooler and brittle, and it is the upper 200, just about 100 kilometers. This happened in the wake of the 1906 earthquake that shook California, San Francisco, and this was a vineyard country, and when surveyors went back and looked at the past record, they could reconstruct it, and they found that at some time when the vineyards were cultivated, when they were first sold, they were all in proper network of lines. But somewhere in between, before the earthquake took place, and this fracture was actually visible, you can see it here on the ground, the earth had actually bent in that region. So it was quite clear that there is an elastic material, which is being subjected to differential stresses, and it is causing it to bend till the strains which are produced in the wake of that bending eventually exceed the breaking strength of the material and it fractures. So that was the time when it became quite clear that whenever there is an earthquake, it's actually caused by a fracture. Tsunamis too, by the way, are caused by fractures in the Earth's crust at the bottom of the sea. And when that happens, then this few kilometers of the water column is suddenly either lifted or there's a differential movement. And it is this movement that causes the ocean scale waves, which as they come to in the open ocean, they are insignificant, just a few centimeters, maybe 10, 15, at the most about 20. But when they come to the shore, that because of the drag effect of the bottom, these are dragged, and the waves shorten their length, and the entire energy is concentrated in one wavelength, and that is why you have this run-up on the beach. So we can see that it is really this fracture which is the cause of tsunami. It's also the cause of earthquakes. Like that. Long before this came to be realized, mathematicians had already laid down the framework of helium elasticity, and it was known that wherever there is mechanical instability in any medium, extended like the Earth is, the energy propagates in the form of two waves. The longitudinal wave with the velocity equal to this, where k is the bulk modulus and mu is the coefficient of rigidity, rho is the density, and shear waves. Because there are two different modes in which restoration of equilibrium can take place, by compression and rarefaction as well as by shearing, and therefore understandably there are two different modes of vibration. And that the numerator there being higher, these waves travel faster than that, and therefore the farther they travel and through the Earth along Fermat's paths, because as we go inside the Earth, the elastic constants increase a bit faster than the density, and therefore the velocity increases, and they bend in the Earth and then eventually emerge at the surface over here. So that is how they bring information about the econometric journey, and also the two waves which travel along that path would fall one behind the other, and that will depend on how far they have traveled. So if there are three locations on the Earth where these can be recorded, and these are the waves here, where you have the P wave and the S wave, and that time difference will tell us how far they have traveled. One can then triangulate and calculate where these epicenters are. And by the 1930s, it was possible to locate most of these earthquakes, and what came as a stunning piece of knowledge was that they were largely confined in these long, narrow belts, which were thousands of kilometers long and no more than about 100 kilometers wide. So obviously, since earthquakes are identified as fracture zones, these are the great fracture zones that girdle the Earth, and as you see over here. And what was remarkable is that within these fracture zones, which almost formed a kind of a region, there were very few earthquakes. As if there was a rigid material, and these rigid materials, and there are a whole lot of them, not a great many, but about 13 if you count the big ones, which fitted the surface of the Earth like a jigsaw puzzle. And it was at their boundaries that most of these earthquakes were located. So obviously they were jostling against each other, maybe moved about by convection on the mantle underneath. And these built up stresses which eventually would create strains that would relax periodically, producing those earthquakes. Those earthquake waves were soon used to do a tomography of the Earth, and one could understand as to how the Earth is constituted in its interior. And it came about that there is an outer surface about 100 kilometers thick, below which the temperature rises to a point where the material becomes a little fluid. So the upper part can be decoupled by this geological boundary, and it can virtually slide or glide over the lower part. And it will get fragmented into spherical caps, and it will go to spherical caps, which being much longer in the lateral dimensions and thickness, began to be called plates. And the bottom line is that after a lot of other data were put together, particularly of magnetic reversals, it turned out that this is the way the Earth behaves. Warm and material that slightly liquefies, melts upwards because of decreased density, and it comes up, it cuts open the upper brittle layer through it, and then the two continental blocks, which are thus drifted, they drift apart, and a new ocean floor builds in between. So, given all that kind of preliminary understanding, and the question is, how do we make sure that wherever we build our buildings, because it is buildings which kill people, not earthquakes. In fact, people run out of their buildings to save themselves from earthquakes. So if we build our buildings so that even if the earthquake comes, nothing will happen, then of course we don't even have to predict earthquake, because it's not an easy job to predict earthquakes. Now we're beginning to realize that they are a piece of critical phenomena, and therefore prediction of individual earthquakes is almost an uncertainty. It is only in a statistical sense that they can predict it. So what's the next thing that one can do? All one can do is what those Japanese did. They calculated as to what will be the maximum ground acceleration from all possible locations of mechanical instability around that region, and then calculate on the basis of this as to what could be the maximum ground acceleration that will produce this. So how do we do that? That's the fracture zone, and here how we can simulate a fracture. This is the ground motion. The Earth does behave to a large extent a little away from the source. I think we are looking at earthquakes which are a couple of 100 kilometers, up to about a kilometer or so, where the material becomes non-linear. The Earth can be treated as a linear system, and therefore one can calculate the ground motion just as a convolution between the material that lies in between where the waves actually start and where we might be over here, for example. So between here and here, if we know the material properties, we can calculate as to what the ground acceleration would be, thanks again to a considerable amount of mathematical theory that has been developed by 19th century physicists, Rayleigh and others. And I showed you the other day how, using inversion of seismic waves, this is something which we produced a few years ago, a picture from the Himalaya to South India. As you go, how does the material look like? And those colors are actually coded for the value of the velocities of shear waves, which in turn give us a value in terms of the coefficient of rigidity of the material there and the density. So one can calculate this. One can indeed do a much finer job, because an earthquake fracture could be several hundred kilometers long and tens of kilometers wide. And what actually happens is that because the Earth is heterogeneous, over this entire fracture plane, the stress does not exceed the breaking strength over the entire one. It's very close to it. But at some point it will just exceed it, and that's where the fracture will begin, and then it will tear, it will move along the entire plane. So it is actually a kind of a source, point source, that is eventually going to occupy the entire fracture plane, moving with certain velocities. And if you want to be realistic, then that is how you have to treat it in order to calculate as to what the ground motion is. Because the ground motion at any point is going to be affected by how this source is moving over this entire plane. All that can be done now. It's not a problem. And that's how, for example, it's been calculated. Colleague of mine and I will calculate it as to what the ground motion would be if a very large earthquake were to take place in the neighboring Himalaya, which is a couple of 100 kilometers away. Indeed, one can do much more, because above the rocky earth, in many places we have sedimentary strata. And you can imagine, that on this on the table, if I put a book and I put a fluffy object, and if I knock at the table, you can easily imagine as to which one is going to vibrate. Sedimentary materials vibrate little more violently than rock, and therefore one has to take into account the fact that there is sedimentary material where the velocity is much smaller, and therefore the energy arrives much faster than it can leave the place, and the material slumps. That is the reason why in many regions which are filled with loose material like reclaimed land and so on, the ground motion is much higher given the same intensity of the earthquake. And this is an example from KOYNA earthquake as to what would happen, how would the ground move, what the acceleration would be if an earthquake of the type that shook KOYNA in 1967 in a region until then regarded as quite safe and stable will actually produce. And one can see that this is 0.3 times the value of the gravity itself. It's a very high acceleration, and it lasts quite, it's like to last a couple of seconds. So all that can be simulated So the next question will be, well, where are these faults and how do we find? If we could find as to where the fault would be as related to my particular site, then I can calculate the effect of each of these faults and build a statistics of what could my ground motion be. In addition, one could put a probability distribution function given some knowledge of how close that fault is to failure as to what could be the probability of the different kind of fractures. We also have a universal indication from the way earthquakes are distributed in time and space, and that is that they follow power law, which gives a hint to us that it's probably a self-organized criticality, and one could use some kind of fractal distribution to generate one's probability functions. So the global context, now I come to India in particular, the global context of the seismic India is currently that it is ramming right into Tibet, but it all started about 130 million years ago when it was the Antarctic and here was India. You see, Madagascar too was a part of India. So this was India. And those materials, those hot materials from the earth below started coming up as sheets of very hot material. They cut through and eventually set India northward. So you see at a later stage, this is what is happening. There was no chasm here. The chasm is widening and being occupied by an ocean. It's wider still, and even Madagascar is going to become separated from here. And this is how India traveled northwards till it came, and it had a long ocean in front of it as it was traveling, and the ocean's rocks have a slightly heavier density. It's about 3,200 kilograms per cubic meter as compared to 27 of this. And so it could easily go underneath the continental Tibet. But the moment all of this ocean was consumed under Tibet, having melted a lot of material and created all those granitic passages that one sees in Ladakh and elsewhere, it could not so easily dive under Tibet because of the high density, because of the equal density to Tibet. But it still continued to run here, as you can see, and over here. So it is this slick plane which gets stuck in the upper parts where the temperature is lower and therefore the material is brittle. It gets friction locked for a while until the stresses behind will adequately to move it.
The joining was actually 10 million years ago, right?
It was about 50 million years ago.
What is that 10 million years?
No, 38 million, 10 million years ago it was here, but then Tibet was also here. Tibet came down to something like, below the south of equator. The whole thing has been pushed back. So it's hundreds of kilometers, about 3,000 kilometers or so that has gone in. And the Indian continent itself has been pushed under Tibet. I'll show you a little while ago, just a picture. So this is the context of Indian seismicity or earthquakes in India. That would take 10 minutes to go. Over here, you see that the encounter is frontal, and therefore most of the earthquakes are in. But this is being pushed from behind, and therefore this entire plate is under stress. So the entire Indian plate, including the ground that you are sitting on, is under very high stress, simply because it's pushed from here. And over there, it is trying to ram into Tibet. The genesis of earthquakes over here is slip across this plane, which already exists. And the genesis here is that it's a 4,000 million years old terrain, which has witnessed many episodes of geodynamic convulsions, and therefore it is riven with lots of fracture zones inside. It's very rigid because the contraction in length between here and if you put a point here in Bangalore, that I shall show you now, and something we started measuring about since 1994, is no more than about 2 centimeters, 2 millimeters a year between here and there. But between here and here, it is 20. So you can see that the strain in that region just behind the front of Himalaya is 20 millimeters in less than 100 kilometers, whether the strain in the rest of India, between the foothills and Bangalore or even Kanyakumari, is just about 2 millimeters in 2,000 kilometers. So the strain rate is very low. Nonetheless, there is some strain which is generated here because there must be some strain reservoirs around fault. This is work which we did a few years ago, and this was looking at this part of the country, going from Agartala to Tawang. You forget about that, those are just waves, which eventually we interpret. But this is what is happening to the Indian plate. It is going down, and here it underlies Lhasa. So you can see that India has pushed it, so it's been pushed right through the Himalaya. The Himalaya is sitting on it, right up to Lhasa, which is, and there it is at a depth of 80 kilometers below this. And this entire thing, even at the foothill, the entire plate descends something like 6 kilometers. So you can imagine an elastic plate bending like this, and what is going to happen to it. And the shape-induced stresses that will build up. And this is a picture which we generated then about the western part, and we see similarly the Indian plate going right up to Karakoram. So there is no doubt anymore that the Indian plate has gone right through the Tibet and right through the belly of Tibet, and its northern boundary, as it was, lies somewhere, if you join the Lhasa line. The stresses are difficult to measure. One can calculate from various other considerations that there must be at least 50 megapascal stresses in the plate itself. So, if there are any fracture zones, small or big, strains are going to accumulate. Those vectors have become available over the last, since 1994, when we were the first to start work in this region. So that's about 18 years. And these are telling us the rate at which that point, for example, is moving with respect to some point in Lake Baikal. And if you reverse the arrow, it will actually mean that it's a relative motion, that Tibet is moving over India in that way. So it is this movement, continuous persistent movement, that piles up strains, and those strains in turn generate stresses, which is the cause of most of the earthquakes here within the interior, because the plate, although it is very rigid, is still subject to a lot of stress, and given any fracture planes is going to accumulate strain. And over here, because of the slip plane between Tibet and India. Those are the experiments done by some Japanese. What they did was they took a piece of granite and put it under stress, three-dimensional stress, and they showed that in the beginning, this is the first stage of the experiment. What is happening is that all the tiny micro cracks, grains, interfacial grains, and all that spaces between them are getting closed up, and you have tiny earthquakes, tiny squeaks everywhere. But then, at some stage, as the loading proceeds, the pore spaces or the grain interfaces close up, but some weak zone that may still exist begins to develop, and finally it is that one which causes the fracture. So these are the various stages of it, and that means that one sees a large number of small earthquakes happening, and then suddenly a bigger. We know that, and that is actually seen in the real world. This is space-time plot of seismicity in the region which is Tokati, Okila, that's the power law of the earthquake, which is universally seen, nowhere ever violated. And this tells us that the largest energy which is available in the strain reservoir is destined to be released with one big earthquake. You cannot dissipate it by a large number of small earthquakes. And that's something which our Indian friends don't understand. I mean, my countrymen, geologists. So, subject constant energy, that's the kind of thing that happens. All that we know is that the failure strain is about 10 to the minus 4. That means you take a 10,000 meter piece of rock, and if you contract it or extend it by 1 meter, then it's ready to go. But you can't tell exactly when because of this self-organized criticality. So, as I said, we can't measure the stressor, but we can measure the strain with high accuracy. And one measures it using GPS, and the accuracy of this has now come down to about 2 millimeters liquid. So if I make measurements, simultaneous measurements at Bangalore, for example, somewhere else, and over the year, I see that over a year, the Indian plate has moved forward by about 45 millimeters. So that means 4.5 meters of strain every year. But that is distributed over a large region. Very little between India, between Kanyakumari and the foothills, but between the foothills and Tibet, almost half, and the other half between that region and by far. One also finds, and this is the measurement we made at Leh and Lhasa observatories, that data is, there's an American instrument taking that data is open to public. Our data, incidentally, is all qualified, classified, and if I share it with you, then I'll be put in prison. Well, I have shared, but not yet put in prison. So you see that this is training, and that's because this entire, the great thing that we found was that from Ladakh, and a friend of ours, Mumbala knows, Peter Borna, was connected with this particular experiment in Ladakh, where we measured these. We find that the convergence rate towards Bangalore always up normally. And that will only happen if this region is behaving like a fluid body. So that was the first indication of the fact that Tibet is advancing over India almost like a fluid body. And this was later on modeled by Dan Mackenzie at Cambridge. So this is what is the Indian plate. We are south of it. And it's going under Tibet. And Tibet is flowing over India normally all along this. And this entire boundary just behind the wall of Himalaya is strained abnormally, and therefore it is extending. So this is the source of all. Now, if we look at the GPS vectors, that means the convergence vectors from far north, far behind the Himalayas into Tibet, coming towards India, we find that over a considerable distance the value is the same, and then suddenly it decreases. And one of the first to interpret this was a man called Roger Bilham, whom Bala knows very well. He's next door to him in Colorado. He proposed that mechanism that Tibet is sliding over this interface. This is the Indian plate which has gone under Tibet, but this Tibet now is moving over India and gets friction locked here, because by the time it has come up here, the material is colder and brittle, until the stress behind increases quite a lot. This is the locked line, which some Americans have done. It is only in Nepal. We have not been able to do this for India because, although we spend a lot of money, but so that's the problem about Indian science that I'm talking about. This is another example of someone in Holland who modeled all available data and said this is the locking line. That means all this is that you see white is the locked region all along the Himalayas. And Tibet is advancing almost steadily right up to the northern limit of this point.
So it's flowing over there because of the pressure of the top.
Yes. India is being pushed by the pressure from what is happening in the oceans, the new oceans. So this is the pressure that we model, and you can see how as it strains for a while, and then eventually this moves forward over here, and the entire Himalayan pile is pushed forward. It lurches over the plains of the Indian plains.
The question was, why does it change from ductile to brittle in that?
Because the temperature. As we go down, the temperature changes. So it slides up to about 20 kilometers depth, and thereafter it gets locked until the pressure of this is recently, a colleague of mine and I, we did an experiment very precisely locating earthquakes in this part of the Himalaya, which is Kumaon, and we find this locking line. This is the region behind which Tibet is currently locked, and that manifests itself very locally in a very narrow belt of earthquakes. So this is again a picture which is produced by Roger Bilham, and it shows how the movement towards Bangalore. I keep on telling Bangalore because that was the place where we first put up our reference GPS station and remains one of the best references because it is connected on a second-to-second basis with the Worldwide Observatory at JPA. So we see how it is locked here, and suddenly this movement with respect to Bangalore becomes much less. So this is the way earthquakes operate. This is the Indian plate. Tibet is moving. Just after a large earthquake has taken place, everything is unstrained, then gradually it becomes strained. It starts releasing some earthquakes, but not big enough. The big enough earthquake will come when this strain reaches about exceeds the 10 to the minus 4 value. And then this point moves over the Indian plains by something like 6 to 8 meters or 10 meters or so. How many we didn't know until very recently.
So just to get some idea, can you name some places on this locked region?
All along, as you go from, let us say, Jammu through Dehradun to Tezpur,
And all of Nepal.
the southern
Parts of India.
Nepal. They're all locked, and it's one big arc, so it doesn't move in one go. It's segmented, and each segment sort of adjusts itself. So these are the earthquakes that we know have happened in the past. But our knowledge of past earthquakes is not very definite in the sense that we cannot translate them into actual numbers of what is the actual energy, what is the seismic moment, and so on. So again, another friend from the US, Bala, I wonder if you ever heard of Jim Bloom from Peter, but Jim Bloom lives in Reno somewhere, and his colleague, he came and looked at this part of, this is just before you begin to enter Dehradun, for example. And he guessed that Indian plate is going down over here, and somehow this Tibetan plate is coming up, and somehow he'll be able to trace this slick plate if he makes a trench around here. So he's a geomorphologist, and just by looking at the morphology of the earth, he guessed that that would be the right place. So he actually did this trench, and lo and behold, he finds this trace here. This is just a few years ago, and he was able then to put this. He also found some vegetable material like tree branches and trapped there, and he dated them. So he finds that there is this slick plane which broke in 1500, and it broke by something like 20 meters. So the slip was 20 meters. That means one huge slip of 20 meters brought forward. So now, if you take a fracture and if you want to slip it, you cannot go on slipping it indefinitely for a limited length. If this slip is going to go on increasing, then the length also has to be much longer. There has to be a scaling relationship, and this is the scaling relationship. Again, I have to convince our Indian geologists that nature has to follow this scaling relationship. This is all the major earthquakes in the Himalaya that have been historically recorded, and there was a friend at Imperial College, Nikan Desh, is a very well-known civil engineer who unfortunately died just a couple of weeks ago. And he had done this, and he calculated from the slip and the information about the earthquake what is the total amount of slip that has occurred in the Himalaya. And this is what his conclusions were. The total strain energy accumulated in the Himalaya over the past 500 years, since that big excavated earthquake fossil showed us, was this much, and the total strain energy which has been released by all earthquakes. So you can see that about 2/3 of the energy that is accumulated in the Himalaya over the past 500 years still remains to be. And these white regions are the regions which are not broken for those last 500 years. So one can imagine I have to move forward. So some time ago we produced these potential slips along different segments of the Himalaya, which could occur any time between now and as critical phenomena cannot be predicted. It's very hard to say exactly when it will happen. But so much of strain has already accumulated there that it seems that nothing will be able to prevent a large earthquake from happening. And if you saw the first picture, that the biggest population density is also around here. I have to move forward. This is the rupture history. Okay, this is the rupture history. 1505 earthquake, which was SEISMIC, and is a result from that tunnel excavation showed, and some other earthquakes. But you can see that in this region there have been no earthquakes over the last 500 years, and that is where about 2/3 of the energy is still remaining. Where people have laboriously made these measurements of convergence rates and across faults, and also categorized this picture from San Francisco, one can see how a probabilistic picture has been produced about what kind of faults with what area and what kind of slips could take place in that region. Now once you have a picture like this, then anywhere in that region you can calculate the ground motion arising from any one of these and then have a statistics. And if then engineers pay heed to it and they make design of buildings to withstand that, then of course we can live into that. So what about the Indian shield, which has been long regarded as being rather stable because earthquakes take place, they are few and far between. Also it's a collage of cratons, which geologists say are the oldest part of the continent, and therefore they have been stable for a long time. But here is an incidence of earthquakes. We compare it with the Arabian continent here, which is also pushing against Iran, and it is virtually pushing at about the same rate as the Indian plate is pushing up against Tibet. This is pushing against Iran, and that pushing is responsible for all the earthquakes in Iran. But Arabian continent itself has very few earthquakes over here, unlike the Indian continent. So it is not enough for a plate to be stressed in order to produce an earthquake. You have to have fracture zones in which those stresses will actually produce strain. Otherwise, the entire stress will just be transferred from one end to the other without any kind of a stress drop. So one should be left in no doubts that within the Indian subcontinent, this very old ancient sheet, which is a collage of cratons, there must be, the null hypothesis would be that there is a fault, there could be a fault anywhere that we know. And because there is a persistent stress, there could be an earthquake of the KOYNA type, which is possible anywhere. So that is the null hypothesis, whether it is Kudan Kalam or here or there. But in some regions, the possibilities are even higher. For example, a colleague of mine put some seismographs recently just in this trigon in southern India, and you see the number of earthquakes everywhere. So small earthquakes are virtually everywhere, and it seems that our older notion that the southern Indian shield is stable is not quite correct. Perhaps it doesn't have the kind of strain rate accumulation as in the Himalaya, but strains do accumulate here nonetheless, because if there were no strain accumulation, there would be no release, and there would be no earthquake. So one can see, one can look for some patterns in continental earthquakes. Along the Himalaya, the patterns were clear, but is it possible to find some patterns here? And what one sees here is that the plate is bent. You know that if you take a piece of metal, aluminium or whatever, and you pull it down here, it flexes. And within the sheet itself, there will be shape-induced stresses. Only with few bars, but here it is. And one sees these kind of stresses actually, this kind of flexure in nature. We also have these fans here, which are deposits brought from the Himalaya of material brought through the rivers, deposited here. But these are not trivial. There's something like 20 kilometers thick, this Bengal fan, and perhaps not that much, but reasonably thick here, also not 20 kilometers thick, has much higher weight than the Himalaya has, which is just 8 kilometers of rock. So even given that the density of rock in the Himalaya is marginally more, you can imagine that both these, as well as the Himalaya sitting at the northern edge of the plate here, have caused the plate to bend. And this bending, in turn, has its stresses. And those stresses will depend on how the plate is bent. Because when the plate is bent, it creates crests and troughs. Now here is a picture of Mariana Trench, which is over here. And the bathymetry, so the plate, the Pacific plate is going underneath here, the edge of Asia, and it has been bent by about 6 kilometers. And you can see how this is the actual topography of the plate, which has actually been measured. So one can see that indeed in nature and the Earth's plates do also bend. Like this. So this is the Himalayan bend, and this is now to scale. And it will create bulges here and troughs, and of course the stresses would be of that kind. This is the surface of the plate, which is bent down to something like 4 kilometers, and these are the stresses, and that's the gradient of the stress. Because Indian plate is moving, so the stresses are also sort of moving along with it. Okay, so it's going to look like this. That's going to be the bulge, that's going to be the trough, that's again going to be bulge, and the KOYNA earthquake, the RUPTURE earthquake, they all occur in this bulge. So it seems that there is a higher susceptibility, even though the faults are not that clearly demarcated in South India, but there is a higher propensity for earthquakes to occur in these belts and elsewhere, and therefore one has to be careful.
Where is JAITAPUR?
JAITAPUR is also in the same belt over here. Also, the South Indian coast, as it moved from Antarctic, and I showed this picture before. Here was Madagascar. This was actually separated when continents are separated by rising sheets of hot materials. They fracture. The upper parts are fractured like this. So these are fractures which are later on submerged by the sediments of the oceans that is created in its wake. That's happened here. So these coasts are carved by faults, and there are faults hidden at their base, which are now covered by sediment. So this should come as no surprise. It should be again a null hypothesis that everywhere on the coast you have a fault. Over here, for example. Now I come to JAITAPUR. This is the regions where JAITAPUR is, and those are some of the earthquakes that not many, but one can see that, and those are from different catalogs that you have found out. Here is a picture where we have a gravity anomaly, which tells us about whether the material has subsided or it has gone up very, very crudely, but of course one can do a very fine analysis because it follows from Newton's law and one can invert it. But this is the gravity anomaly. One finds a big trough over here. You can see the big trough over here, and there are these faults. And so there are faults over here, or at least presumed faults, unless somebody can prove that no, they don't exist, or even if they exist, there has been no activity over there. But there is, and this coincides with a deep trough over here that is very long indeed. And there is JAITAPUR somewhere. J is JAITAPUR. Here again is the JAITAPUR site. That's the fault that I showed. And here is, you can't see it so clearly here, but it's a 20-meter scarp. Now how that 20 meter of scarp come into being? This kind of a feature is produced on the Earth only by faulting. If something has faulted, it may not have come to the surface, but it has come up to here and raised the ground like this. So that's a very strong possibility, unless again it can be refuted.
Erosion can't do that?
Here it is. This is an SRTM imaging. Yeah?
Erosion cannot do that?
Not to that extent. And why in a region, across just a kilometer or a half kilometer? Why should there be so much? So, or if it is, I think that if you are building a 10,000 megawatt power station,
yeah,
you don't discount that possibility. Maybe erosion can be proved.
Yeah.
So maybe trenching of the kind that Vesnusky did in the Himalayas would do this. Maybe looking at termitite deposits, which are different when they are induced by earthquakes isotopically, and some people have used it to look at faults also. So this is the fault here. This fault has been mapped, and this has 20 meters scar. This is the one that goes there. Again over here. So we believe that there are a whole lot of questions that have to be answered about JAITAPUR, where it has been assumed that there is no seismicity, or simply because they have not found earthquakes there in the last 50 years. But then KOYNA and RUPTURE both would have been declared as completely stable for the earthquake. Yes. So the minimum set of scientific investigations which we suggested in the paper after our initial paper was criticized in a very qualitative manner. And that I believe in strategies to earthquake safety in the continent, with so much knowledge around for computing, etc., and making investigations, proving one model or the other one can do that, and internalizing that knowledge then into our life and work, into our practice of constructing buildings and choosing sites.
Thank you very much.
But this is the situation caused by bringing these facts to light. Thank you.
So on the 2nd of January, which was the first day of our Golden Jubilee Conference, M.R. Srinivasan, who is former head of the Atomic Energy Commission, came and exhorted scientists to clarify scientific facts to the public. And I think this sort of thing, I don't think this is what he had in mind, this talk, but it needs to be done. And I hope that those of us who are hearing this talk will, do our own research on it. And anyway, I'm sure there are questions. We proceed.
So this fault along the west coast,
Yeah.
is it of the type that it caused tsunami? Or is it the thrust type which will?
There is a mention of some very stormy weather in 1520 when Vasco da Gama's fleet was in that region. It has not been investigated as to what is the cause of that, but it could be, possibly, it could have been a tsunami. That fact is very prominently mentioned. The date is mentioned, and we haven't looked at it for one reason or the other. But if there is a fault, and that fault causes subsidence of one against the other, then it is a perfect scenario for generating tsunami.
So if there is a fault, is it likely to be of that type or of this?
No, it's not. Because that's how the continents separate, and Madagascar separated from India just along that.
So I have a question about that satellite which measures the strains.
Yeah.
So the strain has to be calculated with reference to a reference state.
No, the satellite allows you to get your position,
Right.
and you make the measurement of position time after time. Okay, so you get U, which is displacement.
U from what time?
No, from any time today, for example. But there are some monuments in this country which were measured in 19th century. We have done that also, and we measured the position today,
I see.
and the change is U. But you can do it from any reference time t, and you measure U, and if you have a large number of points U of R, you can calculate strain.
I guess what Raja is saying is you're actually calculating strain rate. Then you have to.
You calculate strain over a certain period, divide by time, you get strain rate.
So you can calculate the strain rate, and
Yeah.
I cannot.
So as I said, the strain rate in South India between the Himalayan, foothill of the Himalaya here,
Yeah.
something crudely 2 millimeter in 2000 kilometers is about nano strain, 10 to the minus 9
Yeah, but then
per year.
once you got the strain rate,
Yeah.
can you not use some constitutive model from there and calculate the stresses?
Yes, you can. That's how indirectly we calculate this. I said that we have indirect figures of stress, but strains are something which you can measure directly.